Okay, so next I want to talk about the HX addition reaction to a conjugated system, but I want to look at HX addition when we have an asymmetric diene, right? So in our first example, right, we started with 1,3-butadiene. We see that this molecule here is symmetric, right? So we know that there are two products that we can form here, right? And that we can control which product is the major product based on temperature, okay? But in this reaction, we started with an asymmetric diene. Well, what happens if we start with a diene that is not symmetric, something that's asymmetric? All right, so I'm going to draw a asymmetric diene here. Okay, so here we see the molecule is not symmetric, and we're going to kind of ask two questions. If this is treated with HBr at low temp, what is the major product? And then what is the major product formed if we treat this with HBr at high temp? Anything above room temperature. So what would be the major product here? Okay, so let's take a look at this about this reaction here and see if we can come up with the right products that we have here. So it turns out in these asymmetric examples, right, this is not something we can really memorize, right? If I ask you the product, we're going to have to work through the mechanism to figure this out. Okay, so there's not some shortcut we can do. We're actually going to have to go through the mechanism here, all right? And what we're going to have to do is, because these are asymmetric, we're going to have to try to protonate the first alkene in green, and then we're also going to have to try to protonate the alkene in purple. Okay, we're going to have to try to do the mechanisms for both. All right, so let's try the green path, right? We know we can protonate H plus, right? So we can protonate here. So if we take the green path, we can protonate here. And what's really important for us to know is we're always going to form the carbocation. We're always going to put the carbocation so it is next to the alkene. Okay, we always want to have a carbocation that can form a resonance structure. Okay, so it's more important to have resonance versus whether you form a secondary or a tertiary carbocation. We have to always put the plus on the inside so we can form a resonance structure. That's really, really important here, because then we can draw the resonance structure here, and that's the two resonance structures we can draw if we follow the green path. Okay, so first thing we do is we protonate one alkene. I did that in green, draw both resonance structures. Okay, next we're going to see what happens if we protonate the other alkene, the purple path. So if I protonate the alkene at the bottom, again, we're going to add the H to the outside so I can put the plus on the inside so I can draw a resonance structure. Okay? We will then draw the resonance structure associated with that. Right? So I've moved my electrons from here to here to put my carbocation there. So we now have sort of the two resonance structures from the green path and the two resonance structures from the purple path. So now what we have to do is figure out which pathway is more energetically favorable, okay? Right? So what we do is we just compare. In the green path, I've formed a tertiary carbocation, that's allylic. So we have a tertiary allylic for the resonance structure on the left. The resonance structure on the right, that is a secondary allylic. In the purple pathway, I have a secondary allylic carbocation. And then on the right, we also have a secondary allylic carbocation, okay? Which pathway is better, right? The pathway in purple has 2 secondary allylics. The pathway in green has a tertiary and a secondary, right? And we know tertiary is more stable than secondary. So the green path is the path that the molecule is going to form. So we can now ignore this purple path. That is not a pathway this reaction is going to undergo. Okay, so there's 2 options, right? We treated this with HBr, right? So Br now can attack in 2 ways, right? Br can attack in 2 ways. Blue was low temp. The product that's favored at low temp is when you attack the more stable carbocation. So if the Br attacks the more stable carbocation here, this is the product we would form. Double bond, carbon, and bromine. At high temp, we favor attacking the alkene that's more substituted. This alkene is tri-substituted. So if the Br at high temp attacks the alkene that's more substituted, that will get us this product here, and that will be the major product there. Okay, so at high temperature, you attack you form the product, the alkene that's more substituted. This is tri, this is a di-substituted alkene. At low temp, you attack the more stable carbocation, right? So what are the major products that we'd form at low temp? The major product we would form here would be our blue path. We're attacking the more stable carbocation in our green protonation step. At high temp, our major product would be, again, through the green path, right? Through the green path, but we're forming the more substituted alkene. So that would be the major products formed at low temp, and at high temp, this would be the major products formed. So if your alkene is asymmetric, you have to try to protonate one alkene, the other, then compare which pathway is favored, and then take that pathway to finish the product, okay? To finish the product. All right, so I'd like for you to look at an example here. What I'm going to do is draw another example. What would the major product be if we attack this with HCl at 10 degrees Celsius? What is the major product we form with HCl at 60 degrees Celsius? Okay. And I'm going to do the first step for you because I just want to iterate how you have to protonate, all right? This is not symmetric, so I have the alkene in green, I have the alkene in purple. So we have to figure out how to approach this. We have to do our mechanism. So if we protonate the green alkene, we have to remember, right, that we're always going to put the H on the outside and put the plus on the inside. Okay, so the H is going to go to the outside carbon, the plus is on the inside, the plus is closest to our double bond, so we can draw a resonance structure. Very, very important. Okay? If we protonate the purple alkene, right, so this one is our protonation step in green. If we protonate in purple, okay, Again, we're always going to put the H on the outside. H goes to the outside. The carbocation is closest. The carbocation is allylic because we have to draw a resonance structure. So here's the purple path. Okay. We protonate green, draw the two resonance structures. We protonate purple, draw the two resonance structures. Then we have to compare which one of these pathways is better, green or purple. Okay. And then from that, we now have to figure out, do we attack the more stable carbocation or do we attack the alkene, right, that's more substituted after we determine which path we go, green or purple. Okay, so this is a good problem where we can post this to the discussion board to see if we can draw the correct products here.